is my great pleasure to introduce Antonija Oklopcic. And she told me 10 times how to say it, and I still can't get it right. She's here from the Harvard Center for Astrophysics, where she is a Sagan Fellow. Prior to that, she was at the Institute for Theoretical and Computational Astrophysics as a fellow there. And prior to that, she got her PhD at Caltech. What was that, 2017? And she's very excited that she's moving to the University of Amsterdam very soon, like later this year. I don't know exactly when. To be a professor at the Institute for Astrophysics there. Today she's going to talk about, she's going to talk about exoplanets, atmospheres, but she's done a wide variety of computational astrophysics stuff, from clumpy galaxies to intergalactic medium studies, Raman scattering and exoplanet atmospheres. And today she's going to talk about, as you can read, probing the upper atmospheres of exoplanets, focusing on atmospheric escape, and in particular a line that can be used as a diagnostic for atmospheric properties. So with that, take it away.
Thank you very much for the introduction, and thank you for inviting me. Yeah, it's been a really awesome day so far. As mentioned, I will be talking about the escaping atmospheres of exoplanets. So just a brief introduction on exoplanets, as most talks on this topic start with. In the last 25 years or 20 years, we've seen a tremendous progress in this field. With now there's over 4,000 known exoplanets since the first discovery here in 1995, for which the Nobel Prize was awarded just at the end of last year. So clearly one of the fast-growing fields of astronomy. And if we had to summarize, probably in one sentence, what have we learned about exoplanets is that they're everywhere. Pretty much there's, on average, almost every star in our galaxy contains a planet. And they're quite diverse. And they're diverse probably in more surprising ways than we anticipated originally, before the discovery of exoplanets, when we had only one planetary system, which is our own solar system. So it turns out that the most common type of known exoplanets is shown here in this. So this is a diagram that shows the radius as a function of orbital period. And we see that there's this huge pileup here with size between Earth and Neptune. And we call this population mini-Neptunes or super-Earths. And we don't have such an example in our solar system, but clearly it's a very common outcome of planet formation. So this is one of the probably most exciting and unexpected results in the last decade or so. Another unexpected result was probably that a large fraction of known exoplanets orbit their stars at very, very close separations. So we call these close-in exoplanets. So here, this plot shows mass as a function of period, and just to guide your eye, I put this vertical line at 10-day period, and you can see that there's a huge fraction of known exoplanets within that short period. And if you think about the physical environments of these stars and the conditions that they are exposed to, they're very, very different than planets in our solar system, because these close-in planets experience very, very strong irradiation levels. So this plot shows irradiation relative to Earth, again as a function of period. And here's Mercury just as an example. And you see that there's a huge population of planets that are exposed to extreme levels of stellar radiation, up to 10,000 times the level that we here receive on Earth. And so clearly these planets are living in very different conditions, and we would like to know how that affects their formation and evolution. And ultimately, kind of the big picture goal of exoplanet science is to characterize and explain this large diversity that we see in exoplanets, and ultimately use that to learn about how they form and evolve. And one important formation process, or one important process in planet formation and evolution, is atmospheric escape and mass loss. So basically, pretty much all atmospheres are losing some fraction at some rate. So even our own atmosphere is escaping, but not very fast. So we don't have to worry about running out of air anytime soon. So this figure here shows Earth in the Lyman-alpha, in hydrogen Lyman-alpha filter. So this was taken by a commander on the Apollo 16 mission. So here in red, you can see the large corona of hydrogen that is surrounding the Earth and escaping from our planet. So, but in these close-in planets that are very, very close to their stars, the type of atmospheric escape that happens can be very, very different and can be much more efficient than what we can observe here in the solar system. So just the basic picture, and we call this mode of escape hydrodynamic escape. So the basic picture, just to have in mind of the physical process that happens, is that if you have these close-in planets that are very, very close to their stars, they're exposed to extreme levels of X-ray and UV flux, they absorb this radiation, they heat up, as a result they expand, and they then, as a result, can absorb even more, and basically the atmosphere becomes unstable, so it's no longer in hydrostatic equilibrium, and there's a planetary outflow. It's basically driven by thermal pressure, and so it's a thermal process. And this as escape process can be very, very efficient, and people have suggested that the amount of gas that escapes from a planet can be quite a significant fraction of the total mass of the planet, so that it may have evolutionary important consequences for the demographics of all the known exoplanets. So, so some of the potential consequences of atmospheric escape in close-in planets are the so-called sub-Jupiter desert or Neptune desert. So if you look at this diagram that shows planet radius as a function of semi-major axis, there's this population of hot Jupiters, and then at very close periods or semi-major axes, there's this smaller population, but there's a clearly visible gap in between. And this gap is this desert. And it cannot be explained by kind of biases in detection methods or anything, because there's no really reason to expect why we would be able to see the smaller planets but miss out on these intermediate sized planets. So something must be, some physical process must be carving out this gap or this desert. Another clue may be hidden in the so-called radius valley. So it's when we go to look at smaller planets, so again in this planet size versus now on the x-axis is stellar intensity relative to Earth. This is a figure from Fulton et al. That's quite famous now. And it shows, observationally we can distinguish between two populations, and then there's the so-called radius valley in between that's more sparsely populated. And theoretical models of planet formation and evolution that include atmospheric escape actually predicted this kind of distribution even before the first measurements like these were made. So this is kind of believed that this is again an evidence of atmospheric, the impact of atmospheric escape on the overall evolution of planets. But I should also point out that there are other mechanisms that have been proposed to explain this. So I think the jury is still out there. But yeah, these are definitely observational motivation for why we want to study atmospheric escape, because it seems that it might be evolutionary, very important for close-in exoplanets. But there are still many, many open questions. So in a lot of these evolutionary models, people use a relatively simple prescription for how mass loss rate depends on various properties of the planet as a host star, and typically it includes some kind of, so it depends on the stellar flux, radius of the planet, mass of the planets, and then usually there's some heating efficiency that cannot really be calculated from first principles, or maybe can be estimated, and typically it's between 1% and a few tenths of percent. But we don't really know what this number is, and we don't know how it depends on various properties of the system. Does it change with the properties of the planet, how it changes with the properties of the star? Also, what flux here exactly are we talking about? Is the mass loss dominated by just X-ray flux or UV flux or a combination? Is it the same region for all types of systems, or does it vary? Also, how this whole process depends with age. So, anyway, many unknowns that we would like to understand better. And again, what is then the contribution of other types of atmospheric escape? So at what point do we transition from being in this hydrodynamic regime, and when is Jeans escape, which is a much less efficient escape mechanism, more appropriate? How important is contribution of various non-thermal processes? So as I mentioned, hydrodynamic escape is a type of thermally driven process. So all sorts of non-thermal processes, so which include charged particles and interactions with magnetic fields. So at what point they become important? Also interactions with the stellar wind, or from the solar system we know they can be important. So all these things need to be tested on exoplanets as well. And I think the best way to actually test all these relations that people are using in evolutionary models and find answers to all these questions is by observing atmospheric escape in action, so as it happens. And kind of the goal of my work and kind of the whole motivation for this talk and what I will be talking about for the rest of this talk is what we're trying to do is directly measure mass loss rate in a large and diverse sample of exoplanets. And we hope that by doing that, we can try to empirically test these relations that have been derived theoretically and that people have been using, but they have actually never been really tested on exoplanets. So that's kind of the big picture goal. So how do we measure escape mass loss rates in exoplanets? So first, if we want to look at evidence of atmospheric escape, we need to look at the uppermost layer of planetary atmospheres, and the best way to do that is to look at planets as they transit their host stars. So just a quick reminder of what happens when we do transmission spectroscopy. So as a planet crosses in front of the stellar disk, if we observe the transit in various wavelengths, we can see differences in the transit depth as a function of wavelength, and this gives us information on the opacity of the atmosphere at those given wavelengths. So if we want to probe these high up regions, so the uppermost regions of the atmosphere, we have to do transmission spectroscopy at very specific wavelengths that correspond to strong atomic transitions, because that allows us to probe this gas that is very, very low density. And basically the most direct evidence that we can find of gas actually escaping from the planet is if we find evidence of gas outside the so-called Roche radius of the planet. So this tells us this is basically the gravitational sphere of influence of the planet, and if we, in transmission, find evidence that there's gas extending beyond that radius, then that's a really clear evidence that that gas has escaped, and it's no longer gravitationally bound. And actually, the first evidence of such of this escape material has been found quite some time ago. So in 2003, which was only a few years after the first discovery of a transiting planet. So it's quite interesting that we've known of escaping atmosphere for so long. And the most direct evidence came from Lyman-alpha transit spectroscopy. So, and since 2003, this has now been done for a few planets, and they're all listed here. So exactly, I guess, 4 planets. And so what happens is, this is a figure from Ehrenreich et al., 2015. So this figure shows the Lyman-alpha flux of the host star, this is GJ436b. In black line is the spectrum, Lyman-alpha spectrum of the star out of transit. And then in red is the spectrum of the star in transit. So while the planet is transiting the star. And you can see, especially here in the blue wing of the line, there's this huge decrease in flux. So this is basically, I think, more than 50% decrease in flux. And the interpretation is that this light has been absorbed by this huge cloud of hydrogen coming from the planet that is obscuring basically half of the stellar disk. And I should point out that in, doesn't want to go back. Okay. Here, this inner region close to the line center, it cannot be observed in Lyman-alpha because of the absorption by the ISM and contamination by geocorona. So I'll come back to that later, but this is why it has this shape that it has. So this is for the same planet, but now looking at the light curve in Lyman-alpha and in the optical. So this is basically time from mid-transit, and again, flux from the star. And first, if we just look at this solid black line, here during the transit, it has this little bump, like it goes down. I don't know if you can even see it in the back, but this is the optical transit, so broadband optical transit. So the whole planet is obscuring less than 1% of the stellar disk, and that's why it's such tiny decrease in flux. Whereas these data points and the blue curve show the light curve in Lyman-alpha, and you see that it's really enormous. So it goes down to half the original flux, and it extends for hours and hours after the original transit. So the picture, this gives us the picture of this hydrogen cloud, which is really enormous, and it extends far out from after the planet. Now, but there's a problem, and I already indicated that there's many challenges with Lyman-alpha observation, mostly due to absorption by the ISM. So the inner center of the line, maybe plus or minus 30 kilometers per second, cannot be observed, even for the closest systems. So this plot here shows Lyman-alpha spectra of stars as a function of column density of ISM between us and the star. And this is the dark red is basically column density that we would expect roughly towards alpha Cen, so basically our nearest system. And we see even for that are 1.5 parsec. So even at our closest neighbor, basically everything that's here gets absorbed. And for systems that are even farther out, say 10 parsecs or so, it's even worse. So we really can only probe these wide wings of the Lyman-alpha line. And when we go back to what that tells us about the geometry of this wind of planetary escape rate, we see that here is a result of the simulation for that same planet and the wind, and it extends very far out, but the gas that it's actually probed in the wings of the line, so at velocities of 50 to 100 kilometers a second, is this gas that's very, very far from the planet. So because originally the material is launched from the planet with velocities that are roughly equal to the speed of sound, which is for these atmospheres something like 10 kilometers, maybe 20 kilometers per second, but we can only observe them at 50 or 100, which means that this gas was somehow processed to get to those velocities. It was additionally accelerated, and we can only see that gas. So the point I'm trying to make is that Lyman-alpha is not really a clear probe of this inner region where the wind is actually being launched, but it tells us a lot about this material that is very far out and that has been highly reprocessed somehow. People have also looked at other lines, in particular lines of metals, and they found also evidence of these extended strong transits that kind of point also to the picture of the hydrodynamic escape, because in the hydrodynamic escape picture, if the outflow is so strong, then these heavier species basically get dragged along with lighter species and get lofted up to higher altitudes. and just by observing them is kind of a smoking gun evidence that a hydrodynamic escape is happening. And this has been seen for a few systems, but again, there are many observational challenges. Again, basically there's one telescope that can do these observations. I mean, same as for Lyman-alpha. A lot of the host stars are very faint intrinsically at these wavelengths, so it's very hard measurements to make. And also, there's more contamination by stellar activity the shorter you go to wavelength, the shorter the wavelength. So basically, as the start of my postdoc, I was trying to answer a question, are there any other lines that we can use to study these extended atmospheres, but that would not have all these challenges that I was talking about? So basically the requirements, so what would be a good line? And the requirements are that we need a line that is sensitive to a low density gas, so we need a line that corresponds to a strong atomic transition, but we also want a line that's not heavily affected by the ISM. And ideally, we would really like something that's accessible from the ground, so we don't have to write HST proposals every time we want to observe. And it turns out there is such a good candidate, and it's a helium line around 1 micron. So helium atoms are really interesting because they come basically in two configurations based on the relative orientation of their spins of their electrons. So they can be anti-parallel or parallel, and so we call this singlet and triplet configuration. And these two configurations basically live separately. They're not they're radiatively decoupled. And that means that, and the ground state of helium is in the singlet configuration. And that means that the lowest lying level of the triplet helium is basically metastable. We can think of it as almost a ground state of triplet helium, because the radiative decay rate to the ground state is extremely long. Its lifetime is over 2 hours, and this is the longest lived neutral atomic state of any atoms. And another really good thing is that it's very high up relative to the ground state. It's almost 20 electron volts higher than the actual ground state, which means that if we think of this as the ground level, all these transitions are in a much more favorable wavelength range. So they are in the near infrared and optical, as opposed to transitions happening from the actual ground states, which are in the extreme UV, and we can't really hope to detect them. So as I said, from this state, the strongest transition has the wavelength of 1083 nanometers. And this line is well known and has been studied in other contexts, in the context of the sun, stellar wind, outflows from active galactic nuclei. And interestingly, in one of the earliest papers on transmission spectroscopy of exoplanets from Seeger and Saslov in 2000, it was actually proposed as one of the probably easiest lines to detect in exoplanet atmospheres. It was this line and the sodium line. And actually, one paper in 2003 tried to detect this line, but they reported a non-detection. And after that, it seems this line was almost forgotten, because when I started working on this in 2017, there were pretty much no papers after this one about this line of helium. So basically what I set out to do is I wanted to answer a question: can we observe this line in exoplanets, and can we use it to probe these outer regions of planetary atmospheres? And to answer this question, I developed a really simple model of escaping exoplanet atmospheres, which was based on an isothermal Parker wind model. So the assumed density profile looks something like this. So it starts off very similar to a hydrostatic profile, but then it falls off faster. And then there's a radial component of velocity. So the outflow starts slow at low radii, and then it crosses the sonic point, it crosses the speed of sound at a certain altitude, which we call the sonic point. It's called isothermal Parker wind, so it has the uniform temperature. Typically, we assume some few thousand or maybe 10,000 Kelvin, and the initial density is related to the mass loss rate, which typically for these hydrodynamically escaping close-in exoplanets, we consider mass loss rates in the range of 10 to the 9 to maybe 10 to the 11 grams per second. And in that kind of density, assuming that kind of atmosphere, I calculated the level populations of helium. And it's a non-LTE calculation because it's if you basically, the way you populate this metastable helium is through ionization of the ground state and then recombination. And when you do the full calculation, basically you have to take into account the extreme UV photons which ionize helium, and then also mid-UV photons which can ionize the metastable state. So as a result, you get the density distribution, and the helium that's in the triplet state, the fraction is only maybe 1 in a million of all helium atoms are in this excited state. But still, that's enough to produce quite significant transit depths. So the result of the study was the prediction that we can expect to see transit depths of typically several percent. And this is actually quite large transit depths when we talk about exoplanets, because if you look at, for example, absorption features of water, which are now routinely made, they're usually 100 times smaller, so smaller transit depths. So this transit depths of several percent are really huge when you talk about exoplanets. So what this tells us is this helium line can really be used as an excellent diagnostic of these upper atmospheres, and maybe even we can use it to say something about atmospheric escape. But this was all just theoretical prediction, but luckily for me I didn't have to wait long, because several months later there was this paper, the first evidence of helium absorption in an exoplanet called WASP-107b. This was work done by Jessica Spake, who was a graduate student at the time, now is a postdoc at Caltech. She used HST WaveSeq3 data and basically found strong excess absorption in a wide channel that contains the helium line. So the spectral resolution of this instrument is not sufficient to actually resolve the line, but it was a significant excess absorption in this 100 angstrom wide channel, and Jessica did a careful job of basically excluding all other possibilities that what could be causing this line, and she came to the conclusion that it has to be the helium line. But luckily for us, there are many high-resolution spectrographs operating at these wavelengths that can do this much better. So this is just a sample of some of them. And in the last couple of years, there have been a number of ground-based high-resolution detections of helium. And all of these are actually made with the same instrument, high-resolution spectrograph called Carmenes in Spain. And we can see that, I actually forgot to comment on that in one of my earlier slides. Yeah, here. You can recognize this very characteristic shape of the helium line. And I keep calling it the helium line, but it's actually a triplet of lines. And the two components are so close together that they basically merge. And there's a third one that's bluer, that's farther apart, that's separate. So that's why all detections that you'll see later have this characteristic double peak profile. Okay. So again, going back to WASP-107, which was detected by Hubble, now in the resolved detection by Allard et al., we see that it reaches transit depths of up to 8%, which is really huge when we talk about exoplanet atmospheres. So what can we learn from these observations? So basically in the next several slides, I will kind of demonstrate on these a few examples that we have so far, how we can learn about spatial distribution and extent of helium, what can they tell us about gas dynamics, and ultimately how I hope to use that to constrain mass loss rates. So I won't be reporting any mass loss rates yet, because I think there's still a lot more work to do, but I'm kind of hope to describe how I hope we can actually get to those numbers by using this line. So this is going back to the first Hubble detection. because the line was unresolved, all we had basically was the equivalent width. And from that, we didn't really know where the absorption was coming from. And so in the paper, we proposed two models. One was in blue, was the result of my model that I described, the isothermal Parker wind profile that has this double peak shape. And the other model was kind of more a 3D model by Bourrier et al. That was used back in the beginning where I was describing Lyman-alpha transits. So this is that was using their code. So now they use their code to apply it to helium as well. And basically they got this wide, almost comet-like tail of helium. And their spectrum looked much more, had a much wider distribution in wavelength space. So with unresolved detection, we couldn't say what the right answer was, but now it looks like with all these resolved detection that most of the signal is coming from these inner regions that are roughly spherically symmetric. So we're not probing this white tail like in the Lyman-alpha, but we're looking at the distribution of gas that's much, much closer to the planet, but still extended. That also is confirmed by just by light curves, which look quite symmetric. So here's a light curve for HAT-P11 and WASP-107, and you can see it kind of looks symmetric in both egress and egress. We don't have that long tail like we did back in Lyman-alpha. So this is telling us about something about where this gas is coming from. So the only hint so far of a tail or of a helium tail was made for planet WASP-69b in these observations by Nordman et al., where they see a delayed egress in helium by something like 20 minutes. And this is their cartoon of their physical interpretation, is that maybe it's roughly symmetric but slightly elongated in the tail. And interestingly, they make a rough estimate of the length of the tail, and it's roughly 3 planet radii, which is roughly similar to the Roche radius of this planet. So for this actual planet, this might be a direct evidence of escape, but as I'll show in the next slide, for most planets that we have helium detection, the helium signal is coming from within the Roche radius. But this is an exception, and it's really interesting, I think. So now going back to HAT-P11, which has a symmetric light curve, just from the extent of the transit. So here it's 1.5%. If we just assume that the absorption is coming from an opaque annulus, that puts the extent of the helium atmosphere to about 2.2 radii. And the Roche radius of this planet is maybe, I think, around 8 planet radii. So this is not a direct evidence of atmospheric escape like we had in Lyman-alpha, but I still think that by using modeling of these lines, we can still find indirect evidence of atmospheric escape. And I will try to explain how we propose to do that. So basically, using models, we can derive, by assuming various gas densities, velocities, and ultimately mass loss rates, we derive spectral shapes, line shapes, that are all basically unique. And by finding a best fit to the data, we hope to constrain these parameters. And even though we're probing the gas within the Roche radius, if we find a significant outward component of the velocity, this tells us that this gas has to go somewhere and has to escape. So one thing that we find from modeling the line is that if we just try to assume a hydrostatic atmosphere, the line shapes don't fit. They're just much too narrow, even when we assume very high temperatures. So thermal broadening does not do the trick. But instead, if we assume a Parker wind, which has this outflowing component of velocity, the line gets broadened, and it fits the data much better. So here I give the parameters of the best fit, but still I think there's a lot more verification that needs to be done before we can actually claim that this is the mass loss rate. Yes?
Are all those isothermal?
Yes, this one is isothermal, yes. Now you can be saying, well, the line doesn't have to be broadened just by an outflow. You can have different kinds of motions that can broaden the line. For example, you can have what I call horizontal wind, or circular wind, or I don't know. It's basically this motion. And you're right, you would be right, absolutely. So it's probably some combination of these motions that is broadening the line. But I think we have a way to break this degeneracy with observations. Because if we look at the full transit and not just combine all observations into an average transit, but actually consider each individual spectrum, we can actually probe different slices of the atmosphere as the planet is transiting. And basically, this will result in, if there's a strong component like this, this will result in velocity shifts between the leading limb of the planet and the trailing limb. And this has actually been seen in some of the Carmenes spectra. For example, in this result by Solz et al., they report separately their ingress spectrum, so that's this phase, mid-transit, and their egress, and they see this quite significant velocity shift. Now, this is still quite noisy data because Carmenes is on a 3.5 meter telescope, I think, or 4 meter telescope. But I think with maybe repeated transit or with bigger telescopes, we can constrain this much, much better. And this is a work that I have been doing in collaboration with Lynn Hillenbrand and Jessica Spake from Caltech, where we've been using NIRSpec, a spectrograph from Keck, to look at a few of these planets and actually improve the signal to noise and actually be able to use each individual exposure basically as a separate spectrum and break that degeneracy in gas motion. And here I just like to show when we do average in transit and out of transit, you can see that there are error bars here. They're just so tiny that you can barely see them. And so by eye, you just see this excess absorption in the helium line in transit versus out of transit. So basically by using the power of Keck, we hope to do this really much better. So this is all just preliminary, but in our preliminary data, we see the shifts between the first part of the transit and the second part, and now Jessica and Len are still working on really trying to tease out as much signal as possible and really make every photon count so that we can do this in great detail. So parallel in working on interpreting observations, I think there's a lot to be done on the modeling side in terms of understanding more complex geometries and velocity structures and see how we can observe them in spectroscopy. So this is a project that I've been working on with Morgan McLeod, who's another postdoc at the CFA. So we're developing 3D hydrodynamic, well, ultimately the goal is to make them magnetohydrodynamic. For now, they're just hydrodynamic simulations of planetary winds and stellar winds and their interaction. And at the moment, we're not trying to self-consistently launch winds and study how winds get launched. We're just basically putting them in by hand. The question that we're mostly interested in at this moment is to get a realistic velocity and distribution of this gas so that when we do radiative transfer post-processing, that we see how we expect the spectra to change as the planet is transiting across the disk. And we hope to do that first in the helium line, of course, but also there are now other lines that we can use. And I think this is really the way we should be going with this, because one line is modeling just one line is of course limited by all the assumptions we need to make about the composition. But ultimately, if we can connect observations across multiple lines, we can form a complete picture of an outflow. So here, if we can measure all these different lines that have been detected, and some of these lines have now been detected in the same planet, which is really exciting. And I think they probe slightly different regions of atmosphere. So for example, sodium and potassium lines probably probe the innermost regions, and then the H-alpha slightly higher up, and then helium even higher, and then ultimately Lyman-alpha probes this far tail of the wind. And if we can connect all these observations across different lines and they give us a coherent picture, I think that's probably at that point we can claim that we can measure mass loss, right? But so it's still a long way to go until then, but I think that's probably the most promising way of how we can observationally actually constrain mass loss. Now, as I mentioned in my beginning, my goal is to measure mass loss rates in a large and diverse sample of exoplanets. So can we actually, where should we look to what kind of planets or host stars to actually find, more specifically this helium signal? So this is a plot from a recent paper that tried to kind of make some sense from when do we see helium and when we do not see helium, because also some people have now been looking for helium in a lot of planets, and there are some non-detections reported. And it seems that one thing that all detections have in common, or most of them, is that they orbit around K stars. And there's one detection around Sun-like star, and then non-detections around A, M, and this is again a Sun-like star and an M star. And so I was trying to explain why that is. What makes K stars particularly favorable hosts? And I think it has to do with their the spectral shape of their radiation, because the helium line originates from an excited state of helium that needs to be radiatively populated. So basically how it gets populated is through photoionization of the ground state and then recombination into the triplet state. So the photons that drive this process are over here in the extreme UV. But this metastable state can also be directly photoionized through mid-UV photons that are over here. So basically it's a competition between these two processes. So in order to have a large population of helium in this state, we need a fine balance between flux in this band and in this band. So we want a lot of these and not a lot of these. And it turns out that K stars have exactly the right spectral shape for this to happen. So again, here I tested, if you just assume a spectrum, take a spectrum of, I think this was a K1 star, and artificially just boost its high energy end, and let's say this is caused by stellar activity, you increase the population of this metastable helium. So this line shows what fraction of all helium atoms are in this excited state. So the higher, the better the signal. So obviously high energy flux helps. But now I kept that part fixed and I just varied this low energy part, and we see that if we increase this part of the spectrum, the fraction of helium that's in the metastable state goes down. So again, it's kind of the right balance between flux in these two bands that drives, that determines the population of helium in this metastable state, and turns out it's highest for early K stars. And I think that's probably what explains the trends that we're seeing. So it seems that it's not, I would say it's not impossible to have fine helium around other types of stars, but all other things being equal, I think if a planetary atmosphere is around an active K star, it will be most easily detectable. And so this is something to keep in mind when we compare detections and non-detections, because a non-detection of helium does not necessarily mean that this planet doesn't have a puffed atmosphere. It just might mean that it's not in a favorable radiation environment to have a lot of excited helium. And finally, the last thing I would like to point out is that our knowledge of the stellar spectrum is really important for modeling ultimately mass loss rates. And this, if we cannot constrain that well enough, I think this in the end might be a limiting factor, because what I'm showing here is for the same star, people have used, so we cannot observe extreme UV flux for other stars. What people do usually is reconstruct that part of the flux either from Lyman-alpha observations or from X-ray observations and using some kind of coronal models. And in this paper from Bourier, they demonstrate two different ways of reconstructing EUV flux for the same star, and they show that you can get very different results. And so I apply these two input spectra on my model, and again, I get very different results for the helium line. And this would, even though it's the same star, the only thing that was different was the reconstruction method. So ultimately, this would result in different interpretation and different mass loss rates. So I think it's really important that we get more reliable EUV spectra of exoplanet host stars. And so I'm at the end of my talk, so I would just like to summarize. So atmospheric escape seems to be very important as for the evolution of planetary atmospheres of close-in planets that are exposed to extreme levels of high-energy radiations, because this particularly efficient form of hydrodynamic escape, which is caused by this intense radiation, might be able to completely transform planets from gas-rich into gas-poor planets and form these features in the exoplanet demographics that we observe, such as the sub-Jupiter desert or the Radius Valley. But the one way to really test all our evolutionary models that usually assume very simple prescriptions for how mass loss rate depends on various parameters is by observing atmospheric escape in action and actually measuring mass loss rates for large and diverse samples of exoplanets. And even though we have known about atmospheric escape for a long time, the first evidence from UV or Lyman-alpha transmission spectroscopy was way back in 2003. Those measurements were very challenging, and now in the last few years, with especially using this helium line that's in a much more favorable range observationally, we can really start doing this for larger samples of exoplanets. But of course, the spectrum itself doesn't really tell you what the mass loss rate is. To do that, you need to do a lot of theoretical modeling to interpret these spectra. And again, we need very reliable UV stellar spectra to make these interpretations. So thank you very much.
Thank you for a fascinating talk.
Hi, Bill. Hi, everyone. So are young flaring M dwarfs, do they produce enough EUV to potentially populate the helium line?
Yeah, that's a great question. So in this study where I had M dwarfs, I used M stars from the Mussel survey, and their stars were all purposefully chosen not to be active and not to be flaring. So if I had a good spectrum of an active star, maybe I could have a better answer. But yeah, all these stars are actually are chosen because they're not active. So yeah, maybe.
Hilda?
Their standard spectra, EUV ABLEO, that is an active star that you could use. So it exists.
Yeah.
But I would be careful on a number of things that you said.
Okay.
So maybe we can talk later.
Okay.
For example, this thing about the desert of planets in this mass radius area. There's other theories that
I think I said that there are
the
other
formation. I wasn't here at the beginning.
Oh,
so
sorry.
I apologize.
Yeah, I said it's just one of the proposed theories.
Okay,
I did say that there are other.
Right. And the nature of the EUV, it also depends on the coronal model that you're using. So not only versus coronal and from Lyman-alpha, but also from exactly what coronal model you're using and how good your X-ray data is.
Sure.
So, and this issue of the case study will be interesting to see your paper because you already see in HT209 that is a G0 star.
Yeah, I mean, I think I said that it's not impossible. I think all things being just that K stars seem to be most favorable, but I don't think it's impossible to have detect helium around other types of stars. I mean, clearly there's a detection around HT209.
Andrew, then Roger.
Yeah. So obviously, as you said, the stars that have the highest or had the highest mass loss rates probably don't have atmospheres anymore. So I'm curious where these four that you found the helium in has been found in Like, where are they relative to these photo evaporation
Yeah.
valleys?
I'm trying to make sense of that myself. So some of them are so if you look at the desert, like let's say this, some of them are on the upper edge of the desert, but also some non-detections are on the upper edge of the desert, and also some are on the kind of the lower end. So there doesn't seem to be a clear rule where they're all kind of close to the desert.
From what you
but
expect, right?
yeah,
So-
but also interestingly, there's few non-detections on the upper edge of the desert as well. So yeah, I'm still trying to make sense of that.
Question about the diagram there. You said that most of the triplet state excitation comes through photoionization and then recombination. Is direct electron excitation unimportant?
It's included in my code, but it's subdominant.
Do you just include the thermal electrons, or do you have superthermal electron excitation?
I don't have superthermal, no.
So I think that's the most important term in the Earth, for example, in populating 10830. And there'll be superthermal electrons in all these atmospheres.
Okay.
So maybe something to think about.
Okay.
Yes, we'll
So you mentioned you have a few systems that show multiple transitions from different ions. Do you think these ions come from completely different regions, or could there be enough overlap in velocities or position where you can actually try to start constraining the actual composition of these atmospheres?
I think it will probably depend on this it will vary from system to system, but I think probably there's going to be so for example, there was a paper that came out last Friday that sees quite comparable transit depths in, for example, sodium and H alpha, but in some systems I think H alpha might be overlapping with helium. So yeah, I think it will just vary, but yeah, hopefully there'll be some overlap, which would give us a nice test that we can connect them all together.
Any more questions? If not, let's think.